तो और भाई कैसे हो? पिछले 2-3 दिन से बाहर था यार, तो डे 2 ऑफ स्ट्रीक अगेन फ्रॉम 110-20 समथिंग। सो लेट्स सी व्हाट डू वी हैव टुडे। कल तो इजी क्वेश्चन था तो मैंने नहीं बनाया, बट आज देखते हैं अपन क्या है। आज तो 2 पॉइंटर स्लाइडिंग विंडो का क्वेश्चन है, इंपॉर्टेंट क्वेश्चन है। इंपॉर्टेंट क्वेश्चन नॉट इन द सेंस कि इट्स टफ फॉर समथिंग, इंपॉर्टेंट फ्रॉम द इंटरव्यू पॉइंट ऑफ पर्सपेक्टिव. This 2 pointers and sliding window are one of the most asked questions in the interviews. So we'll see 2-3 approaches for this question. So let's start. Let's start by reading the question. Let me write also the constraint first. Uh, Constraints are basically s less than 100. So this is the one constant. Okay. तो अभी क्वेश्चन में क्या गिवन है? We have given a binary string s and a positive integer k. Okay. And a substring s is beautiful if the number of ones in the substring is exactly k. That means whatever binary string we have given 100110101, and let's say k equals to 3, then for a substring to be beautiful the number of ones in it should be 3. For example, this is beautiful, this is beautiful, this is beautiful, this is beautiful, then this is beautiful. Like every substring that has count of ones equals to k will be beautiful. Now let then length is the length of the shortest beautiful substring. Okay, and we have to return the lexicographically smallest beautiful substring. That means, say in the above case, this is the one right that has four length of 4, right? Correct. So 1101 length equals to 4. Then there is another one. One, no, there is no one, I think, other than this. Okay, there is one only. So only this will be answered. Now let's assume if there is another one that says like 1011. Now then if both have same length, the smaller one, right? This one, which one is smaller? This one is smaller, right? So this will be answer. Now lexicographically smaller. So this is the entire question. Now constraints are very small, like up to the 100 only. So even if you run a like for loop basic brute force approach is very simple, right? For I equals to 0 till n we go. The next loop will go for j equals to I till n. Then now you have a substring, right? Now in this you can count once. If equals to k, then check for answer. So this is the brute force approach. Then what is the time complexity for this one? This one is of n cube. Y n cube. This step, and this matching step. Okay, this is pretty much simple. Now let's do one dry run basically. Let's take one example. Okay, let's build one example so that we can get both equal case as well, right? 1 0 1 0 1 1 0 1 1. Okay, so so now let's do a dry run. Now let me ask you one question now. So you answer one question. If I start from left, what happens when I move to right? See what happens when we move to right. What happens when we move to right? क्या हो रहा है basically? If you can answer this question, you can easily understand all of the 2 pointer approaches. So tell me, basically ones increasing, right? Count of ones increase, and what do we need? Count of 1 equals to k we need, right? So now at any index, right? At any index, what happens, right? See, if if 0, then count remains same, right? Now if 1, then count increases by 1. So either we can have count greater than k, or we have count equals to k, or we have count less than k. Only these three cases are possible, right? Right? Now we will see these cases later after dry run. Why I told you this case before dry run? Because this is one very important observation for all of 2 pointers or sliding window questions. You need to know what happens when you move forward. So if there is a particular thing that keeps on increasing or decreasing, that means if you increase its left pointer, you decrease the sliding window, the opposite will happen. That's why you need this observation. So now let's do a dry run. So 1 0 1 0 1 1 0 1 1, and our k equals to 3, right? So initially when I'm I equals to 0, this is my substring. Here I will do count, right? Count equals to 1. Substring become 1 0. Count becomes still 1. Substring become 1 0 1. Count becomes 2. Substring become 1 0 1 0 1. Count becomes 3. If it becomes 3, our answer will be right 1 0 1 0 1. Now, when I move ahead, you see my count becomes 4. See, count becomes 4. And if count becomes 4, that means now it is invalid situation, right? Invalid scenario. We need count only equals to k. That means now what we are going to do? Now we are going to shrink it now, right? From the left, when we move to right, number of ones increase. That means if we move, if we bring our left closer, that means number of ones will decrease. So we'll remove this, right? So our string becomes 0, 1, 0, 1, 1. Count becomes 3. And this is now a valid answer, right? And which one is smaller among these? It has length equals to, this one has length 5. Now this one, right? 0, 1, 0, 0, and this one also has length 5. But which one comes lexicographically first? This one, right? So this is your answer now. This one is your answer now. You can either compare or you can use the string matching functions. In Java, you can use compare to. In if you are in C++, you can simply just do less than greater than 1. Okay. Now, see, still you have count less than, right? Count equals to k. So that means you can further move it. So you can do now 1, 0, 1, 1. Count is still 3. If count is still 3, this 1, 0, 1, 1 is less than above. So our answer becomes 1, 0, 1, 1. Now, you will again remove 1. It becomes 0, 1, 1. That means 2. Now, if now our count becomes less than k, that means this case. That means now you again move forward. So what we did, count greater than k, we do left increase, right? If count equals to k, then also we increase our left. We increase our left and we update our answer. Now when count less than k, we move towards right. Why we move towards right? Because we need more k now, more 1 now. Now, then after that what will happen? Where is that white color? Okay. So after that, what will happen? 0, 1, right? So you go to again 0. See, count is still 2. 0, 1, 1, 0, count 2. So no contribution to the answer. Then next is simply 1, right? 0, 1, 1, 0, 1. Now count becomes 3. But since our answer is already smaller than it, so our answer remains 1, 0, 1, 1. But now our count is 3. That means you can increase your left now. So if we can increase our left, we remove this one, it becomes 1, 1, 0, 1. Still 3. Now our answer will be what? See, among 1, 0, 1, 1 and 1, 1, 0, 1, which one is smaller? I think 1, 0, 1, 1 is smaller, right? So that means it will be our answer. So now we are at the end basically. So this is our answer. So this is the entire sliding window approach. And you see, when you move, you only traverse all position at most 2 times, right? Not n times, at most 2 times only. So time complexity will become of n plus n. N basically for left and for the right pointer, which is effectively of n only. Okay. So this is the sliding window approach. Now, in this of n is the for the sliding window, this string comparison, right? Comparison also takes like of n. So total time complexity will be of n into n. So this is the final time complexity. But you see, this is important. Whenever you solve a sliding window problem, you should know what happens when we move from left or when we move towards right. If you know these two simple answers, you can solve any sliding window 2 pointers approach question. Now, how to identify if it's a sliding or 2 pointer? That is simple. The answer basically is for a particular window, and you can, when you look at the question and you read the problem statement, see, is your with your window, does your counters change or no? If yes, that's a 2 pointer question. So this is the now we will do one optimization on it. So you tell me first if you have any optimization. There are two optimizations, but one of them is like generic and one of them is very specific to this problem. See, you see, since n is less than equals to 100, right? N is less than equals to 100. That means what? Each position can be represented as an integer, 128-bit integer. Each position can be represented as 128 integer, 128-bit integer. So that means any substring, we can have a integer for it. You set bits, right? You set bit, you unset bit based on your like whatever your substring is. That means now comparison will take what time? So your comparison will become basically now of 1. Anyways, just let me tell you, this is also kind of n only. Why? Because n is approximately 100 only now. So so this comparison will take of 128-bit. So this is actually greater than of 100. So people say it's an optimization, but this is not an optimization actually. This is just a way to avoid string comparisons. But the effective time complexity of this one will be still greater than the string ones. Now, let's see what happens if the n, right? If n is like 1e5, then what happens in this case? Sorry, n less than equals to 1e5. In this case, we have like of n square, right? Now, of n square is not going to work in this way. And now, how can you optimize this? There are two things. First is, there are two cases. First is 2 pointer. Can we optimize it? Can we optimize? And the second was string comparison, right? So we need to answer if we can optimize both of them separately. So 2 pointers can be optimized. In the question, we always care about the position of ones, right? We only care about position of ones. That means we can pre-store, right? We can pre-compute, right? We can pre-compute position of ones and only consider them. So this will remain of n, but the problem is it will, if your string is very sparse. Sparse means there are a lot of zeros and a very small number of ones. Then it will become significantly smaller. For example, 0, 1, 0, 0, 0, 1, 0. In this case, your effective string will become only this one, this position, that is 1, 2, 3, 4, 5, and 5 only. This will be your final position, 1 and 5. Only on this you have to run the loop now. Now, second is string comparison. How can you compare the strings effectively in of one time complexity? Using hashing. First, you need to pre-compute hash, right? Pre-compute hash of each substring, each string prefix. Prefix is better. Of each prefix, we'll say each prefix. Then for a right for a, if you need hash of L comma R, you will say hash of L comma R. You can say prefix of R minus prefix of L minus one. But this is not simple. There is some factor as well, right? Some multiplier. I don't remember that multiplier right now. But if you Google it, you can easily get to this string comparison approach. In that way, your final time complexity will become of n. So this will be your final time complexity. And string comparison will then take off one only. So if constraints are, and I'm definitely sure someday this hard part of this question will come and they will give us this constraint only. So if you can have this string comparison approach, then you can simply compare in off one. Yeah. For the code part, I'm not going to code. I want you to solve this question. See, you can see the code now. There is no problem, and you can see code anywhere. Like you can ask ChatGPT, you can ask any AI. But the problem is you should know how from pseudocode how you can reach to the code part. That is why I'm skipping the code part. You try to solve it by yourself. Then you try to write this string comparison or hashing one. If you can solve both of these, very good for you. Very good for you. If you can learn this hashing one, you can at least solve like some hard question on the lead code easily. Thank you.